functions and a couple of properties of functions that we really want to make sure we know what they are. So first, let me review the definition of functions. A function f is a subset of a cross b such that the domain of f is a. All of a must be used. And if x, y, and xz are in f, then y must equal z. So this is the vertical line test. Some vocabulary we use: if a equals b, then we will say f is a function on a, just like we did with relations. The notation will have f colon a arrow b. This means it is a function, period. I might also say mapping. F is a mapping from a to b. Mapping and function are the same thing. If a is the domain, then b is the codomain. It's not necessarily the range. Range is whatever gets spit out, not where b is all possible things. It's where you're going to, not necessarily all the things you hit. So two properties we care about with functions are one-to-one and onto. First, let's look at one-to-one. In an intuitive way, the way I think about one-to-one is your a doesn't get squished. This is especially true in something like linear algebra, where you have vectors and things actually do get smushed into things. Each a, little a and big A, has a unique little b and big B. Now let's look at a couple of examples. You've got A1 going to B1, A2 going to B2. Each A has a unique B. So this is one-to-one. Here we've got A1 and A2 both going to the same B. So this is not one-to-one. Now size is sometimes important. If we look at something like this, I've got A1 going to B1, A2 going to B2. Looking at it like that, it is one-to-one because each A has a different B. I could have made this squished. I could have made A1 go to B2, and then it wouldn't be one-to-one. So it doesn't matter that B is bigger. It can be one-to-one if it's bigger, if B is bigger. However, if B is smaller, there's no way it can be one-to-one. You must get some squishing to get all of A into B. We will refer to this as cardinality. Cardinality is going to get really freaky next week, but for today, this week, the cardinality for finite sets is just the number of elements. But in general, to make the statement, if the cardinality of A is bigger than B, then it can't be one. The other property we will look at with functions is onto. The idea of onto is everything in B gets covered. So the range of your function is actually all of B. Your codomain equals your range. A couple of examples. I've got B1 gets hit and B2 gets hit, so then this is onto. Whereas over here, B1 gets hit, but B2 doesn't, so this is not onto. These are the same two functions we use for one-to-one. Here's an example where A is bigger. A can be onto because it's bigger. It doesn't have to be. I could have still plotted everything to B1, but this is onto because both B1 and B2 have a pre-image. Whereas here, there's no way this can be onto because B has a larger cardinality than A. Let's do a quick overview of some things we need to keep in mind with functions. So f is a function from A to B. To be a function, every little a in big A must go somewhere. A little a in big A can only go to one B. It can't go half here, half there. A little b in big B can be gotten by more than one A or no A's. To be one-to-one, little b in big B can only be gotten by one A or none at all. To be an onto function, every B in big B must get at least one little a in big A. Okay, now with that under our belt, let's look at the formal definitions of one-to-one and onto. First off, one-to-one. A function is one-to-one if and only if, whenever xy and zy are in f, then x equals z. So this should look a lot like what we did with to define what it is a function. Because when a function is one-to-one, that means its inverse is a function. So that's why what this looks like is kind of like the flip of what we have for what a function is. Another way of looking at this, using our more natural notation that we're more used to, is I can say if f of x equals f of z, then x equals z. This is typically how we're going to prove something is one-to-one. If it is one-to-one, it is also called injective. I tend to forget to say that. I tend to say one-to-one because it just makes more sense to me. Injection, like injection, I guess that could make sense too because you're poking it in and you're not squishing it. Anyway, whatever helps you mnemonically remember it. For example, let's say we've got 2x minus 1. This is a nice, pretty line. I graph it. I can see that it passes the horizontal line test, which is another way of doing the one-to-oneness. I want to prove that it's one-to-one. So I say, okay, well, assume f of x1 equals f of x2. So 2x1 minus 1 equals 2x2 minus 1. I add 1 to both sides. I divide by 2. Ta-da, x1 equals x2. Therefore, f of x is one-to-one. Here I look at this and I go, it's clearly not one-to-one. To show that it's not one-to-one, all I have to do is show a counterexample. So f of 2 equals f of negative 2, which equals 5, but 2 does not equal negative 2. So it's not one-to-one. So now we'll look at some theorems. If f is one-to-one and g is one-to-one, then the composition is one-to-one. You just said it, but shorter than what it said. So the composition of one-to-one functions is one-to-one. So let's prove this. Assume f and g are one-to-one. Now I want to show that the composition is one-to-one, so I want to assume that g composed with f of something equals g composed with f of something else, and then show the insides are equal. G composed with f of x1 equals g composed with f of x2. Well, rewriting what that composition means, that's g of f of x1 is equal to g of f of x2. So I've got g of crap equals g of different crap. Since g is one-to-one, their insides must be equal. Now I've got f of something equals f of something else. Since f is one-to-one, their insides must be equal. So I started off with the functions g composed with f of x1 equal g composed with f of x2 and got down to x1 equals x2. So therefore, the composition is one-to-one. If f and g are functions and their composition is one-to-one, the only way a composition can be one-to-one is if f is one-to-one. If f breaks at the beginning, then the whole thing can't happen. So let's prove this. We're assuming f and g are functions and the composition is one-to-one. To show that f is one-to-one, I start with f of x1 equals f of x2. Now I know that the composition is one-to-one, so I need to massage this so it looks like a composition. Well, if f of x1 equals g of x1, I can do g of both sides, because g is a function. So g of this equals g of that. But that's just the composition. So if the compositions are equal, their insides are equal. So I started off with f of x1 equals f of x2, got down to x1 equals x2. Therefore, f is one-to-one. So now I want to look at the formal definition of onto. Function f going from a to b is onto if and only if, for all little b in big B, there exists an a in big A such that f of a equals b. This is also referred to as surjective. If you know any French, surjective, sur means on. So you're kind of mapping on to b. Onto means all of b is going to be in the range. So let's look at one of these theorems. If f and g are onto, their composition is onto. So let's start with suppose f and g are onto. To show something is onto, you grab something from the codomain, just a generic average Joe element, and say, okay, whatever here in the domain gets mapped to it. You construct it. You can't just say, well, here 2 gets hit by this and 5 gets hit. You need to be generic. So I'm going to say, let's little c be an element of big C, because I want to show that the composition going from A to C is onto. Well, if little c is in big C, since G is onto, I know that there's a B such that G of B equals C. Well, since F is onto, I know there exists an A in big A such that F of A equals little b. So that is the A in the domain that will be mapped to the C in the codomain we care about. Therefore, the composition of onto functions is onto. So if f and g are functions and the composition is onto, the only way that's going to happen is if g, the second function acting, is onto. So let's prove this. Suppose f is a function, g is a function, and the composition is onto. I want to show g is onto. So I take a generic element in C. Well, since the composition is onto, I know there's some A in big A that gets mapped all the way over to C. But for the composition to get mapped to C, there has to be some stepping stone in the middle. Rewriting this expression, I have f of g of a equals c. G of a has to be in B, so there's my stepping stone. G of a is in B, so we found an element that gets mapped to C, therefore it is onto. So we'll practice with some of these in class, but those are the two main topics we care about, one-to-one and onto. These are used a lot to show that two sets are quote unquote the same. Depending on what class we're in and what algebraic structure we're looking at, determines what other properties we have to show. But almost all of our isomorphism or homomorphism or things where we're showing this is the same as that and whatever structure we're looking at starts off with showing that something is one-to-one and one-to. And I think that's a really good place to stop. Thank you.